Hello everyone, my name is Jungwon Kim. I'm a professor at Korean University. I'm so sorry for missing my trip to Jeju Island. I think nowadays Jeju Island might be very beautiful, so I'm very unhappy to miss my trip to there because I have some meetings or some discussions at my own university. But next time, if available, I will be at Jeju Island for this conference for sure. Thank you again for the invitation, and then let me start my presentation here. So the title is Multi-Agent Deep Reinforcement Learning for Connected and Autonomous Vehicle. So when you look at this figure, you can see my research partners. At Korean University, we are with Dr. Soi Jung and PhD students Wonjun Yoon. And then this project is also correlated with Hanyang University ITRC project. And then we are working with Jaehyun Kim at Aju University, Marco Laborato at UC Irvine, and David Moisen at University of Central Florida. So based on tight collaboration with international researchers, we made some progress. So maybe in the end of this slide, I would like to introduce our research results in terms of multi-agent deep reinforcement learning for autonomous and connected vehicles. So first of all, let me introduce base concept of DRL, deep reinforcement learning, and then I would like to introduce policy-based multi-agent deep reinforcement learning. And lastly, I would like to introduce the applications of multi-agent deep reinforcement learning in terms of connected and autonomous vehicles. Then let me start with our basic concept of DRL. So maybe most of us are very familiar with reinforcement learning, right? So suppose that we have one agent here, and the agent has working on top of the state. So within the state, it is gonna move one by one. So now current position is 3.4. This is a Cartesian coordinate. So the agent is located in the position. So within the position, this agent will make an action, and finally it wants to go to this final goal. Okay, then it's gonna make connection, right? So it can go to the north, it can go to the west, east, or south, or the other some much more various directions. So suppose that we have these kinds of 16 different actions here. So based on the action space, this agent will make an decision to the next state, and it will go to the next state, and so forth. And our ultimate goal is that this agent should be in the final destination once we are done for the reinforcement learning procedure. So in conventional deep learning, we have a lot of algorithms. We have some classifier, we have linear regression, we have classifier, we have some recommendation system or such like that. But in most of deep learning algorithms, we are focusing on one-time decision. But if you are talking about the reinforcement learning, it means that we want to make a discrete time stochastic decision making per unit time. So every single unit time we will gonna make a decision. So it's not for one time decision. We have some kinds of decision sequences. That's why one of the famous deep reinforcement learning algorithm is called Markov decision process, because we don't have one time decision, we have sequence of the decisions. That's why we are saying that we are working with a decision process. Okay, so here our objective is arriving at the destination, and then what the agent can do here, it has some directions in terms of action spaces. Among given these 16 directions, they will make a decision again and again, and finally it will arrive at our destination. That's our ultimate goal. So this kinds of decision process is a core nature of reinforcement learning. That's why we in wireless network or wireless communication systems, we have dynamics. We have queuing dynamics, we have channel state dynamics, we have a lot of dynamics. So depending on the dynamics, we have to make a decision every single time. That's why reinforcement learning algorithm is very powerful for these kinds of communications or networking systems. So now, suppose that the agent is located here. Okay, and suppose that agent is located here, and then suppose that we are in S sub 1. This is our current status. Okay, and then this is our possible action space. So in our previous slide, we just note that we have 16 different actions in our given problem. So we have 16 different actions here. So every single action at state S sub 1, we have different number of quality values. Among these given quality values, we select one which guarantees the maximum reward. And then we will make a decision for A sub 2. And then suppose that with A sub 2, this move to, for example, S sub 2. Then we are here. And then we will compare the reward again, and we will gonna make another decision, and then we will jump to another state, and so forth and ever. Then we will gonna arrive at our desired destination. So we are doing the iterative computation until the scenario is terminated. Okay, and then these Q values can be also denoted as reward. That's why we can make a notation just like that as well. So here we have some concept that is called trajectory, which means that suppose that we are in S sub 0, and then by taking the action as A sub 0, and then we will take the reward of S sub 0, and then we will move to another state that is called S sub 1, and so forth. And we will gonna make a decision again and again until we are in terminated state. So our objective function is that we will gonna do the summation of our reward, that is also called cumulative reward, and then we have some discount factor which is denoting the reduction as time goes by. So our main objective is about to maximize this given cumulative reward function. That is the main concept of reinforcement learning. And then, okay, this is selected here. But we have some problem. So in conventional reinforcement learning algorithm, for example, Markov decision process, which is one of the famous one, in Markov decision process, we can solve the problem with dynamic programming. But as we all know that dynamic programming takes a lot of high computation overhead. So in terms of algorithmic theory, the computational complexity of dynamic programming is pseudo-polynomial, which means that if our number of states is quite small, then it is possible to get the optimal solution for sure. However, our state is very larger, then in the case it takes a lot of time to get the solution. Now we have some trouble over here. So in AlphaGo or something like that system, we have a lot of state. We have Go playground, and over there we have to make a decision again and again. So it has a lot of state. That's why we have some trouble in terms of to get the solution in a polynomial time with the dynamic programming. That's why we start to think about the neural network about that. So previously, in order to solve this problem, we used the dynamic programming. However, it takes a lot of time. That's why we have some approximation function here. This is called deep neural network or deep learning framework. So in deep learning framework, we have a lot of dense layer, which is also called a hidden layer. And then based on that, if a state is given, then we will gonna make a train based on the data set that is associated as a states. Here we have action. So once we are done for the training with a lot of state and their corresponding actions, then this neural network can make an approximated optimal solution. For example, if we put some state here, we're gonna make a computation here, then we're gonna get the computed approximated actions. So once we are done for the training over here. So that's why based on this deep neural network architecture, once we are done for the training with a lot of data or a lot of time, then based on this architecture for the inference phase, when we have our current state, then we can get approximated action. That is the main concept of deep reinforcement learning. The name is deep reinforcement learning because we are solving reinforcement learning algorithm with a deep learning framework. That's why the name is deep reinforcement learning. Yes, this is talking about that. Now we start to have these kinds of the neural network. So based on the neural network, we have a lot of states here, and we have a lot of actions here in order to make a training. And once we are done for the training, the variables or weight factors are trained here. And then if we have new state here, then we can get the optimal, neo-optimal approximated actions. then we can immediately get the action once we have state. That's why we can make a much faster decision making based on this neural network architecture. So now, based on this result, we want to argue that why we need multi-agent system. So that is called policy-based multi-agent deep reinforcement learning. So now we want to talk about the multi-agent system. So here, this is the game, what we are talking about. So first of all, we have our given state. This is our given state. Based on the given state, we have to make an action. So here we have a lot of enemy in the top, and we have our agent in bottom. So we want to make a play, and then we want to make movement on top of our given agent. This is our given agent. It has go left, it has go right. It depends. We have to find the optimal actions over here. So if we have a lot of enemies here, maybe make an action to left hand side might be better. Maybe making an action to the right or left hand side also be better. We don't know yet. However, this agent will make a decision based on its trained parameter. But now we have to assume that two agents have same state. Then we have to define that do they optimally act. It means that they are agents, they have same reward function, they have same action set. Then when the given state is the same to each other, then their action might be same because they have same reward function, same state, everything is same. That's why their action should be same as well. But in that case, they will be identical, which means that if this one move left hand side, this one also goes to the left hand side. If this one goes to the right hand side, this will go to the right hand side because they have same reward function, they have same state information over here. That's why they will act identically. Okay, but there is no meaning in terms of the multi-agent system because they act the same. In multi-agent system, they should be cooperated or they should be coordinated. Then someone should go left-hand side, someone should go to the right-hand side, and they have to shoot their enemy in both sides, then they can be maximum. However, if they act identically, then we have no meaning at all. It's just the same with the single agent movement. That's why we need cooperative multi-agent system in order to design cooperated and coordinated multi-agent systems. So here, this is why we need multi-agent reinforcement learning. Someone should go to the left-hand side, someone should go to the right-hand side in order to make a coordination and cooperation. So that's our main objective here. So here, this is the basic concept how we can realize these kinds of multi-agent reinforcement learning. So here we have one neural network architecture. As I told you before, in order to make deep reinforcement learning, we have state information here, we have action information here. But in this case, we have two agents, right? And two agents have same different state informations. And then they will be trained with one single neural network. And then their action, the first one is for the agent 1, the second one is for the agent 2. And then the two agents are trained with identical single neural network. In this case, during the training phase, their parameter will be mixed all together. So in that case, their parameter will be shared. That's why we have some chance to make them cooperative. This is called cooperative neural network or communicating. So the agents are communicating here. That's why this is called ComNet, which means communicating neural network. Okay, so we can realize multi-agent neural network system with a centralized single neural network using ComNet. Now we have to define how the ComNet works. So in this case, I told you that we have two agents here, two state sequences are here, and their corresponding actions are here. And these kinds of two sequences are trained in a single neural network. That is our basic concept of ComNet model. As I told you before, here two agents parameters are applied, and then their parameter will be mixed all together. That's why we can realize the cooperation. then below we can observe how the cooperation was realized. So suppose that in this illustration, we are talking about the case where we have 4 different agents. This is agent 1, this is agent 2, this is agent 3, this is agent 4. So when they have their own parameters here, and this parameter will make an impact to the other agent's information proceeding. So in that case, we have mean operation in order to mix the variables all together, and finally they are merged all together, and then we can define the variable for the next hidden layer. And then when we have these kinds of the procedure and the parameters in each agent should be mixed all together, that's why we can realize the cooperation. So in this case, we have 2 agents here. Their agents parameters are numerically encoded at first, okay? And then we have communication variable, and then we have activation functions. So we can explain this one more details with some illustration. So instead of introducing these kinds of complicated equations, I want to explain this one in some illustration. So before starting the illustration, let me note that this paper was published in 2016 NeurIPS. The name of the paper is Learning Multi-Agent Communication with Backpropagation. This paper is famous in multi-agent cooperation, multi-agent deep reinforcement learning with a centralized single neural network. So in this case, we have to define the communication variable at first. So suppose that we have 4 different agents here, okay, and then they have single variable, their own variables here, and then in a first agent, the second value, third value, fourth value will arrive here as well, and they will be averaged. And this is the averaged value for the other agents. In a similar way, in A sub 2, this is second agent, we will get all the information for the others. That's why we get the information from A sub 1, A sub 3, and A sub 4. And then we have new value, this is from the others. And agent 3, we get all the information for the others. That's why we get the information from A sub 1, A sub 2, and then A sub 4. That's why this is the value for the others. And lastly, here, A sub 4, we get all the information from A sub 1, A sub 2, A sub 3, and then we have the variable from the others, okay? And then you can observe that this information is our own, and this is information from the others. And then we are mixing together, and then we put this one into activation function. And then we can get one value. This is the value for the next step hidden layer. So up to here, this is for hidden layer 1, then this is for hidden layer 2. Okay, and in a similar way, this one will be averaged, and then they will be in the activation function, and we can get the value for the next hidden layer. They will be averaged, and then they will be in the activation function, and then they will be in the next hidden layer. Same way, they will be the next hidden layer. Then we can mix the information all together in order to realize the communication. So this is same. So this is the application of the activation function for the next step in our computation procedure. So in here, I want to show you the computation procedure in a single illustration. Suppose that we have hidden values. Okay, as I presented in previous slide, this is for first agent, this is for next agent, third agent, and fourth agent. We define their own hidden variables. And then for the first agent, from the others information, we make communication variable. We do the same thing for the second one as well. In the second agent, we gather the information from first, third, fourth, and then we make a communication variable. For third agent, we get the information from the first, second, and fourth, and then we make this one. Lastly, here we get the information from here, and then we gather all the information from the others. That's why we make the communication variable. And then these communication variables are organized with the information from the others. That's why this is my own, this is the others. That's why, as I presented before, we mix all together with the activation function, and then we define new hidden variable at time t, and this is at time t plus 1, which means that hidden layer t plus 1, and so forth. We move forward with this procedure. Then we can consistently mix the information when we proceed. So this is the ComNet. But as you can see here, in ComNet, all 4 agents are sharing the information with the mean operation or activation operation. But in computation procedure, you can observe that there is no difference between them. Their weights are all same to each other. So in hidden layer 1, it calculates its own data with its own or the others, and the others mean, and they will be mixed together, and that's it. We are doing same thing in each agent. That's why the computation procedures are all identical, which means that there is no weight on top of the agent. Sometimes one agent is very famous, very important. Sometimes the relationship of 2 specific agents are very strong or the others are very weak. But this kind of nature cannot be applied or cannot be modeled with these kinds of ComNet. So ComNet is only meaningful once we can assume that all agents are identically equivalent. Then ComNet is very powerful in that case. So in graph approach, so our proposed or our target ComNet algorithm is meaningful only when all the agents are equivalent. So should the agent communicate with all agents? My answer is that's yes. Can it transfer only one essential information between agents? No, the information should be shared all together. Okay. But sometimes people want to make some more sophisticated algorithm in order to define the relationship much more precisely. So for that purpose, we have a new algorithm that is called G2ANet. Okay, with the G2ANet, we can design some more sophisticated communication or computation relationship. So this is G2ANet. So in G2ANet, so in previously, in ComNet, all the agents are identical, all the agents are communicating all together, and the weights are all the same to each other. But as you can see here, the first agent has no relationship with the first one. They have no relationship. Okay. And as you can also see here, 2 and 4, they have no relationship as well. Even though this one has a relationship with this one, the weights are different. This can be much more stronger than this one, or vice versa. That's why we can design the much more precise agent relationship with some graph theory. So G2ANet will be the solution for this problem. Okay. Actually, G2ANet was proposed by this paper, Multi-Agent Game Abstraction via Graph Attention Neural Network, which was published and presented in ICAIIC 2020. So you can observe that this kind of algorithm is quite new, just 1 year before today. That's why it's quite new. That's why it's very interesting, and we have a lot of variances nowadays. So now we have to decide how we can make these kinds of the multi-agent cooperation. So in this case, the nodes in the graph, the vertices are agent. So we want to make a relationship among the given agent with one graph. In a graph, we can define the edge if they have some relationship among the agent. If we don't have edge here between 3 and 4, it means that they have no relation. Okay. In addition, in 1 and 5, they have edge cost C. In 1 and 4, they have edge cost as B. And then C can be much more larger than A, which means that the relationship between A and 5 is much more stronger than the relationship between A and 4. That's why we can define these kinds of relationship very precisely. That's the main concept of G2ANet. Then, now, we have to clarify how we can do that. The first of all, we need a two-stage attention model. For the first attention, we can define the graph. So here we can make a graph with the first attention. So which can be realized, which can be eliminated. We can make a binary decision between the existence or non-existence. That's the first step in this G2A net. So that is called hard attention. So based on the hard attention, we can make a relationship at first. Okay. So this is our initial graph here. And then with hard attention, we can define the edge. Okay. And this can be eliminated. And this can be eliminated. This can be eliminated. Only we have this one, this one, this one. And then we are defining the edge over here. And then we apply the attention model one more time for soft attention. Then based on the soft attention here, we can set the weight values on top of the edges. This can be 100, this can be 10, this can be 1. Which means that the relationship between 3 and 4 is much weaker than the relationship between 1 and 2. That's why we can define the weight factors on top of the edge by using soft attention. So let me note that in order to make a relationship with the edge for the first time, then we need hard attention. Okay. So briefly and summary, so we have graph among the given agent, and then we are applying our hard attention at first, and then we will move to we can define the graph over there, and then based on that we apply soft attention again in order to set the variables on top of there. That's the main procedure of G2A net. So we can see some more details about that in this slide. Okay, so we have 3 steps here, actually 2 steps. First step is just the graph relationship representation. So second step is our first step, the hard attention. Okay, so when we have encoded data here at first, and then we have to pass the hidden layer at first, since this is related to RNN, because this is time series decision making in some game algorithm, which is targeting by this paper ICAIIC 2020. That's why we consider RNN. But the key point is here, hard attention and soft attention. This is for the graph relationship making. This is for defining the weight on top of the graph. And then based on that, we combine the result, and then we can make a decision over here. This is the main architecture of G2A net. So, as I told you previously multiple times, we have state and we can define the relationship given this graph based on the hard attention. Okay, this is for hard attention. So this is much. So for the hard attention computation, we have these kinds of softmax, and then we can define the adjacent matrix in order to define the edges. So in this case, this can be connected 0 and 1, and 1 and 2, and 2 and 4 are connected, 3 and 4 are connected, and so forth. So then we can make a directional graph based on this adjacent matrix. And based on the result, we apply the soft attention. So when you apply the soft attention, we can define the values. Those can be used for the weight factors in graph. And then we can make a score. Score can be sourced to compute the weight vectors over there, and then it can be scaled, and then we can apply we can use the attention model in order to get the values. So this is our result for the soft attention. Then we can use this value for defining the weight on top of the graph. That's why finally we have hard attention output. This is defining the graph. This is soft attention output. This is defining the weight. And then we are doing element-wise operation. And then when you are doing the element-wise operation, 0, 0, this is 1, this is 1, this is 1. The others are all 0. That's why 0 components are eliminated here. And then you can pick the element. Those are computed with 1. So this one is here, this one is here, this one is here. Because they are computed with 1. They can be arrived, but if they are multiplied with zeros, then they can disappear. So this is called element-wise multiplication. Okay. So then we can define the edges and then we can define the weight over there. That's called G2A net. So now we're gonna see how the ComNet or G2A net can be applied to our connected and autonomous vehicle applications. So first example was a co-work with Professor Daehyun Choi at Jungwang University, and this work was by my master students Myung-jae Shin, and then this was published in 2020 in Transactions on Industrial Informatics. This is for charging scheduling, electric vehicle charging station problem. So these are the charging station, electrical vehicle charging stations. So they are kinds of the fuel station. So they have some ESS, energy storage system, and then they have some energy over there, and they can make a energy source transfer to the electric vehicle if they are coming. So then if the energy here is not good, is not enough, then we can buy some energy from this utility company. But the price of energy or price of electric energy is time varying or is based on the auction in the local energy market. That's why we have to decide when we have to get the energy, which can be the cheaper than previously, or we have to define the sharing of the energy amounts among these given electrical vehicle charging stations. For that kinds of the computation, we said that every single charging stations are agents, and they have to decide where how much energy should be shared with the others. And that's why every single these kinds of charging stations can be defined as multiple agent, and then they will be designed with a single agent, and they will be designed with the neural network. But in this case, setting the weight on top of a charging station is meaningless because we can assume that every single charging stations are identical. That's why instead of the G2A net, we can use ComNet for this case. So in this paper, we use the ComNet in order to solve the energy sharing problem. So main objective is sharing the energy among these given electric vehicle charging stations in order to save the energy, in order to minimize the purchase from this utility company. That is the main objective for this paper. Based on this concept, we extend this system to autonomous vehicle. So this paper was accepted by Transactions on Vehicular Technology. Now you can search this paper in IEEE Explorer. So this work was co-worked with Professor Jaehyun Kim at Aju University. So here we are considering multi-agent deep response learning based cooperative energy management system. So we have three stages: cloud, edge, and end. In end case, we have UAVs. They are flying, they are doing some surveillance, they are doing some autonomous task. But UAVs are strictly energy limited. That's why they should be charged over wireless power transfer. Okay, so in first task between edge and end, we have to make a charging decision. So charging decision can be solved with some optimization or convex optimization, and then you can define that the scheduling decision between this EMS energy charging station and this UAV. We can make a scheduling decision over there. Then the EMS has neural network and they are multi-agent system and they can share the energy all together, and then we can decide how much energy should be shared in order to minimize the purchase from utility company. Then you can think that this problem might be very similar to our previous one, but we have a little bit difference over there because in previous problem we have electric vehicles. The electric vehicles will select their desired charging station based on their own willing. It means that suppose that I'm a driver and I can find where I have to charge by myself. It's not based on the scheduling decision. But in this case, the UAVs are all unmanned, which means that they should be scheduled autonomously at first. And then the charging decision, which means that where the UAVs should be charged, should be defined by the scheduling algorithm, not from their own willing. That's why there is a main difference between UAV system and electric charging system, electric vehicle system. Anyway, once the UAVs arrives at the charging station, they should be charged. And sometimes this UAV has a lot of big UAVs. This one has nothing. But in that case, they should be able to share the energy sources altogether. That's why we are using multi-agent deep reinforcement learning algorithm. Even in the case, we can assume that all the EMS, energy management system, are identical, which means that we don't need to worry about the case where individual EMS has their own property or own characteristics, because we can simply assume that they are all same to each other. That's why we can just use ComNet for this case as well. So in the paper, we presented a lot of various simulation results over here. That's why if you are interested in this system, I highly recommend you find this paper and read this paper over there. They should be very beneficial. Okay. So let me show you how the ComNet is used for this system. So as I told you before, we have charging stations here. These charging stations, as I told you before, they should share their energy altogether. Okay. Suppose that it has a 30 energy. Suppose that it has 40, it has 60, you have 70. Okay. So that can be the states for each single case. And then we have multi-layer deep neural network. Okay. In this simulation, we use 6 layers over there. Okay. But every single step procedure, as I introduced in ComNet, so we have the values over here, and then if we have in the first agent, this value will be here. The summation or mean of the others should be here. The activation will make a decision for the next step. So this is what we learned, how the ComNet works. So based on this step-by-step procedure, we have 6 different computation based on this ComNet architecture. Then we can make connection. Okay. So suppose that this is 40, this is 50, this is 50, this is 20. Then it means that 30 becomes 40, which means that the first charging station should get 10 from the others. 40 becomes 50, which means that the second station should get 10 from the others. The third should be able to release 10 to the others. The last, 7 to 20, it means that this should release 50 from the own ESS. So in this case, you should get 10, you should get 10, you should release 10, you should release 50. That's why in this case, we have to release 40. Then in that case, we don't need to buy the energy source from the others. That's why we can save our cost over there. So in this case, in order to design the reinforcement learning algorithm for this problem, we have to activate the sharing of the energy among these given ESS, and then we don't need to buy the energy source from outside in order to save our cost over there. That's why here, when you define the reward function in reinforcement learning, you have to facilitate the sharing of the energies. That's the main design for this multi-agent deep reinforcement learning. As I introduced before, if you want to know more details about this one, please read the paper. It should contain a lot of more details design in terms of the reward design, reward function design. The other application for autonomous system is the surveillance. Now we use this ComNet for autonomous surveillance drones. This is by my student Wonjun Yoon and Dr. Sohee-jung, Suyeon Park, and this is a co-work with Professor David Moise at University of Central Florida. So drones can be used for the data delivery, mobile base station, and so forth, but it can be also used for the surveillance. That's why the drones are designed for the surveillance in this problem. Okay, and then the actions are not the amount of the energy anymore. The actions are directions they have to go. That's why we have drone coordination here. So we have to define where we have to go. So X, Y, Z, we have these kinds of coordination. That's why they can make a decision every single time. So that's why this is drone base stations, okay, for the surveillance. And then the training procedure is the same, but we have to keep in mind that the reward function itself is for the distribution of the drones. If they distribute more and more, if they can cover more and more area, then it will increase the reward function. That is the main difference from our design in previous result. So our action depends on the coverage, surveillance coverage in the target area. So based on this objective, we are defining our ComNet. Okay. So next algorithm for autonomous and connected vehicles, we are talking about drone taxi. So this is autonomous drone trajectory learning. So this is also by Professor Jaehyun Kim and David Moisen and myself here, and my students Wonjun Yoon and previous Aju University PhD student Soi Jung. So this is based on the result of multi-agent deep reinforcement learning. Actually, drone taxi problem is very interesting. Suppose that we have 4 taxis over there, they are flying. So drone taxi is loading the passenger and drop the passenger, okay? And it has its own capacity as 3 or something like that, as 4. Because in taxi, we have some driver, but in this case, we have no driver because it is autonomous system. But over there, we can load the passenger 4 or 5. So in that case, so this is a trajectory for the first PAV, personal aerial vehicle, PAV here. And in this case, they will load the passenger here, load the passenger here, and so forth. And loading the passenger should be available only when we have some available capacity, as well as the direction of the destination for all the given passenger should be equivalent. So the passengers in a taxi, they are moving to the almost the same directions. Then it is beneficial to load the passenger. Okay. So in order to calculate this one, we use G2ANet. In previous examples, all the charging towers, all the agents, they are all identical. But in this case, in order to consider much more sophisticated situations in terms of the logistics or the number of passengers or and so forth, we define the agent different altogether, all different. So in this case, we have to consider G2ANet. That's why we use G2ANet in order to design the trajectory for the given multi-agent drone taxi applications. So in this case, among these given 20 passengers, we have outage just like 1, 2, 3, and 4. Except these 4 passengers, 16 passengers were served by these 3 drone taxis. That's why we have more than 80% accuracy for the management. But if we have some random action or conventional algorithm, we just cover 25% passengers. That's why the performance here is much better than our conventional algorithm. So we are doing this research nowadays. So we have several publications related to this one. However, we are writing some journals for this further investigation. So since I speak a little bit faster, these kinds of tutorial finish a little bit earlier, but I'm ready to make a Q&A altogether for more time. So if you have any questions, feel free to let me know. Then we can make a discussion on top of that. Thank you very much to listening to my speech. And then I'm ready for the Q&A. So please let me know once you have any kinds of questions. Thank you.
Thank you.